for NEET is now available on the Google Play Store. Try it out for free.
Hello, friends. Hello, friends. So, today we are going to continue our discussion of rotation. Okay. And first, I will introduce the ideas again, and then I will do a little more with gravitation. Okay. The the ideas in rotation, they firstly they have quantities which have parallels from translation, that is linear motion. Okay? Rotational motion is a alter ego or a sister or a cousin of translational motion, right? Now, it is important to note that finally that there is, in addition to rotation, right, there is the case when there is both. Okay, that case is when you have a wheel rolling, right? That is called rolling, you know, rolling motion. Okay, in rolling, there is both rotation and there is translation. Okay, so you have both a rotational component to what is happening and a translational. Okay, and finally, there is so there are a variety of quantities which show up, you know, and which have related relationships. The rotational quantity and the associated translational quantity have a relationship. Okay, so, and these, importantly, there are the vector quantities, the scalar quantities, and the associated quantities, which are, come from one derives from the other. So, having confused you with that, first let's start again from basic principles. We did two types of products when we started with vectors, right? We came up with the dot product. The dot product of two vectors a and b is a times b times cos of the angle between a and b. Now assume that these two products happen over a period of time. Okay, and let us say, for instance, one of the products, right, um, produces, right, one of the products produces a is a micro entity, that is a incremental entity. So work is f dot ds, where f is a non-incremental entity and ds is a incremental entity, which is the distance moved. You apply a force over a distance moved. The dot product of the two is a vector, right? And that vector is f, is denoted f dot ds, and that integral, or integral, is essentially a summation, right? Now the dot product summation, okay, at every moment, right, you can do an f dot s ds, and the summation of all those dot products produces work. Work is such an essential quantity, right? Because it is related to this quantity called energy. Okay, potential energy is the capacity to do work. Kinetic energy is created by transforming one form of work to another. Okay, So that is the most essential idea. So the properties of dot product A dot B equals B dot A, right? A dot A is A square. The dot product of two vectors produces a scalar, right? And so how do you, if you had A equals AXI plus B AYJ plus AZK, B equals BXI plus BYJ plus BZK, A dot B is AXBX A plus AYBY plus AZBZ, right? Then we introduce a second idea, and this idea is very relevant in the context of rotation. This idea is the idea of the cross product. A cross B, if there are two vectors A and B, right? The cross product of these two vectors is a vector C, which is perpendicular to the plane of A and B. Okay, this is a very non-intuitive idea that the cross product in this case of A and B is a vector perpendicular to the plane of A and B. So if A is this way, B is that way, right? The cross product will produce a vector which is that way. So they typically use the right hand screw rule. Like you'd use your hand, you sweep the A, then you go towards the B, and the direction of the is along your thumb. The direction of the cross product is along your thumb. C equals A cross B, and C is your direction of your thumb. Look at the corkscrew, right? Spin a cork from A to B. The direction in which the screw goes is upwards. Why do they talk of this corkscrew rule? Screw rule. Why do they call it the? Because it is a natural idea of rotation. Okay, they want to teach you rotation by showing you when you what do you do to a screw? You rotate it in order to push it upwards. That is the analogy of it. C equals A cross B. All right. So you curl your hand, right? So just as you curl your hand, you rotate. How does Ravichandran Ashwin, right, bowl his ball? Curls his hand, right? Or rotates his wrist, right? That's how they produce spin, right? So that is the right hand screw rule. There is a natural rotation, and the direction of the cross product is perpendicular to the two vectors. A cross B, the cross product is normal to A and B. So A cross B equals is usually calculated if you had two vectors A and B. We did A dot B, which produces a scalar, just AX BX plus AY BY plus AZ BG. In this case, you draw A cross B is calculated by drawing a determinant I J K AX AY AZ BX BY BZ, and then you evaluate the determinant. Okay, I times AYBZ minus BYAZ. I times AYBZ minus BYAZ minus J times AXBZ minus BXAZ plus K times AXBY minus BXAY. Okay. So once you do these three, you make these three, right? You end up with a cross product. Okay, so this is the core idea of the cross product. Okay, so A cross B is the magnitude is AB sine theta, right? In the previous case it was AB cos theta. For dot product, in cross product is AB sine theta, and the direction is perpendicular to the plane of A and B, right? And you point A in the with the index finger, B with the right, and C, A cross B is the thumb rule. Okay. So A cross A is 0. A cross B equals minus B cross A. It is not equal to B cross A. The associative property does not apply. Distributive property applies. Scalar multiplication applies. So Remember, if theta equals 0, right? A cross B, A cross A is 0, or A cross whatever will be 0, because sine theta is 0. If theta is 90, you get the maximum value. So because sine 90 is 1, right? Now, what is A cross B? Physically, it represents the area of a parallelogram. If you have A and B forming an angle, A cross B is the area of the parallelogram. Okay? So, so those are the properties, right? And I explained how you can calculate. I cross J equals K. I cross and it is J cross I equals minus K, right? I cross J cross K equals I, K cross I equals J, right? So I cross I is 0, I cross J is K, right? I cross K is minus J, okay? J cross I is minus K, okay? So when you go in a circle, I cross J equals K, J cross K equals I, okay? And K cross I equals J. If you go in a circle, right, it is positive. If you go in the counterclockwise direction, IJK, it is negative, right? And then there is the, and you must learn this associative property and become comfortable with evaluating the determinant. See, I explained to the determinant, how to write the determinant, how to calculate it, how to do A cross B, right? And then how to, if you had A cross B dot C, right, it will give you the volume. Okay? A cross B will give you the area, and when you take that vector and you do the dot product, you will get the volume. A cross B dot C will give you the volume. A cross B will give you the area of the parallelogram. A cross B dot C will give you the volume of a three-dimensional parallelepiped, parallelepiped, right? Like puppet. Okay. So now learn all the equivalence. Displacement, angular displacement, velocity, angular velocity, momentum, angular momentum, mass, moment of inertia, force, torque, acceleration, angular acceleration, rotation, precession, like a top. What happens to a top, right? Will precess. Okay, so torque is the moment of the force, R cross F. The moment of the momentum is angular momentum. Moment of force is torque. R cross F is torque. R cross mv is angular momentum. Okay, so d omega by d theta by dt, right? D theta by dt is called the angular velocity, which is also a vector. Okay. Now, when we calculate the angular displacement, remember, is a vector, right? Like that, angular displacement is also a vector. It is the change in the angle of rotation, and it is upwards. If you're rotating like this in this plane, the direction of angular displacement is upward, and hence, when you just divide by delta t is a scalar. So omega is d delta theta by delta t. Rate of angular displacement is the angular velocity, how fast you spin, right? The angular velocity. How quickly you spin is calculated in radians per second. How much angle do you cover in per second? Is radians per second. We do not use degrees per second. Remember that. Okay. So if you do when we can do RPM, right? To go from RPM to radians to angular velocity, right? If you do one rotation per second, it is, you multiply it by 2 pi, right? So one rotation per second is 2 pi radians per second, right? So if you have the period as t, 1 by t is the number of rotations it something covers. It's the frequency, 1 by t. T is the period, 1 by t is the frequency. Okay, 2 pi by t is the angular velocity in radians per second. Okay, so now when something is rotating at a radius distance r, what is the direction of the velocity? What is the magnitude of the velocity? It is rotating in a circle with a certain angular velocity omega, right? So we started with a radians, right? 2 pi by t, where t is the period, 2 pi by t is the omega, right? Now, omega cross r is the radial vector, and the radial vector keeps changing. The direction of the radial vector keeps changing, right? So omega is upwards. If I'm rotating like this, omega is upwards, right? Omega cross r, omega cross r will give you the direction of v. The direction of v is tangential. Okay, so remember that. Okay, omega cross r equals v. People just say v equals r omega. What is the meaning of v equals r omega? Right? It comes from this, v equals omega cross r. Okay, so keep that in mind. V equals omega cross r. Now, when something rotates faster, 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 right? What is happening to it? It has angular acceleration. It is going to give you, make you dizzy, right? I'm sure you've gone in that merry-go-round, right? And some boy will come and make it spin faster and faster and faster. What he's doing is he's adding to its angular acceleration. Alpha. When you add to the alpha, you cause more angular acceleration. The rate of change of angular velocity is angular acceleration. Just as the rate of change of velocity is acceleration, rate of change of angular velocity is angular acceleration. And corresponding to that, see, normally when you just have uniform circular motion, the direction of the acceleration is only radial. We have just uniform circular motion going in a circle with a constant speed. Remember, the direction of the velocity is continuously changing. It is always tangential, right? Now, if you go with the what is the direction of the acceleration? The direction of the acceleration in uniform circular motion is always only radial. But when you go faster and faster and faster and faster and faster, you have two components, two types of acceleration, or two components to the acceleration. You have two components to the acceleration. One component is the radial one, which comes from uniform circular motion, and the other component comes from going faster and faster and faster and faster. That is called the tangential acceleration. So you have the radial acceleration, omega cross v. V equals omega cross r. Omega cross v gives you the radial acceleration. Okay, so you end up with omega cross v, and then you have the tangential component, which is related to your angular acceleration, and that is called the tangential acceleration, that is alpha cross r. Okay, so this is a really confusing pair of ideas. There are two different things that are happening, right? You're going in a circle, right? So when you're going in a circle, let us say you're going in this circle, right? What is the direction of omega? Upwards. What is the direction of r? Radial. Let's say you're at this point, right? At this point, the r is from the center of the circle towards the point. Position. What is the position of the body? From the center of the circle to where the body is, right? So that is what r. If you're spinning like this, your omega is upwards. Omega cross r will therefore be tangential. If you're going like this, omega cross r is tangential, right? Now, omega cross that velocity, that is the gives you the velocity, right? In uniform circle. Omega cross that velocity, right? Omega cross v. Remember, v is this way, right? And if you're going in a circle, v is tangential. Omega is upwards. Omega cross v is again radial and towards you. Omega cross v will give you the direction of the acceleration. Omega cross v is radial. So omega cross r, which becomes omega square r, right, is gives you the, and if they were all perpendicular, perfectly perpendicular, omega cross r will become omega square r. Okay, so omega square r will be radial. Okay, so we say that in uniform circular motion, you have only one component for the acceleration, which is towards the center of the circle in the same direction as r, right? Now, when you go faster and faster and faster and faster and faster, you have a second component to the acceleration, right? So omega cross r is the radial acceleration. The second component of the acceleration is alpha cross r. Okay, that is a, when you go faster and faster and faster and faster and faster, you have a second component to the acceleration, alpha cross r, which is tangential. The net acceleration is a sum, vector sum of these two perpendicular vectors. The vector sum of these two perpendicular vectors is, so AR plus AT. Remember, AR and AT are both vectors and perpendicular to each other. So when you have AI plus BJ, right, you just write it as AI plus BJ. So the net acceleration is the tangential acceleration plus the radial acceleration. Okay, so that is the complexity of just the acceleration, in the context of rotation. But if you understood this, the tangential acceleration, the radial acceleration, right? So look at the picture, radial and the tangential. If you understood this radial and tangential acceleration, you will naturally understand the ideas that we are going to present. What does torque do? Torque causes angular acceleration. Tau equals I alpha. Tau equals I alpha. Just like F equals ma. Tau equals I alpha. Torque causes something to have more and more angular acceleration. Spin faster and faster is caused by torque. Tau equals I alpha. Okay. So having understood that, if there is no torque, you can still have something going in a circle, right? Uniform circular motion. And what goes in a circle, uniform circular motion, with just one force will continue to do so. Okay, so if there is a continuing force, single force, right, you continue to go in a circle. Like if you had the earth and the moon will, and there is one force which is towards the center, and the moon is going like that, then it will potentially, under certain circumstances, just go in a circle. In other circumstances, it will go on a circle and it will quickly, under the attraction of the earth, will come into the earth itself and come and collide with the earth. Okay, those are the ideas there. Okay, if it's going beyond a certain speed, it will just be orbiting, and but below a certain speed, it will come into the the orbit of the earth, or into the it'll get caught in the gravitation of the earth and come and hit the earth. Okay. So now when we toss a body, right, motion of a particle in 2D, right, it has two components. Okay, there is a radial component and there is a tangential component. Okay, so you have a V will be both, it will have a r omega times theta, which is the radial component, and then a tangential component as well. Okay, so keep that in mind. Okay, so particle traveling in 2D, r equals r times er. You take the vector derivative, you'll have dr by dt times er plus r times der by dt. That will produce your theta dot times e theta. Okay, so remember this. Okay, and you will then be able to understand how these things get derived. From that, you end up with these two. When you take a second derivative, you end up with these two components when you do uh, the derivatives in terms of the products. Okay, I don't want to go into the details of that, but remember, AR is omega square R, and A theta is, which is the or AT, right? AT is alpha cross R. AR is omega cross R, or omega square R, right? A theta is alpha cross R. So the radial and tangential. If you are in uniform circular motion, a uh, AT is zero. Uniform circular motion. AT is zero. You have only a AR, right? Uniform circular motion. The A is only towards the center. The V is only tangential. Therefore, A equals omega square R. Omega cross is omega square R, or V square by R, because V equals omega cross R, or R omega, right? So V equals R omega, and V square by R becomes omega square R. Okay, so that's all that you need to know. If you understand this, you have understood the basics of rotation. Okay, and I like to teach it in significant detail so that students understand this. Omega equals 2 pi by t. Once you understand this basics of rotation, then it is very easy to, when we introduce moment of inertia. Okay, moment of inertia is, we introduce moment of the force torque, moment of the momentum, which is angular momentum. Like that, we introduce the moment of inertia. Inertia is related to the idea of mass, right? So the moment of inertia will give you the, is the equivalent of mass. Okay, it is denoted as integral r square dm, moment of inertia. Okay, so non-uniform circular motion is when you have an AT as well. Okay, therefore AT is the dv by dt, which, let's say you had a speed where v is the speed, so dv by dt will give you the AT. Fast and faster, the rate of change of the tangential velocity, the magnitude will give you. Okay, so so those are all the ideas. Moment of inertia uh, is is actually said to be a tensor. Okay, but think of it like a scalar. for most practical purposes in high school physics. It is r square, integral r square dn, or mr square. If you have a point body, mr square, where about a particular axis of rotation. But r is about a particular axis of rotation. Okay, so those are all the ideas you need to learn. Now let's look at a simple problem. A body of mass 0.5 kg is attached to the end of a string having a length 0.5. The ball is rotated on a horizontal circular path about a vertical axis. The maximum tension that the string can bear, right, is 324, right? So the maximum possible value of the angular velocity of the ball is what? So T is related to what? A, right? So T F equals ma, right? M is 0.5. 0.5 times A equals T. The maximum tension it can carry is related to the maximum acceleration. What is the maximum acceleration? 324 by zero point 0.5, right? 324 by zero point 0.5. After that, the string will break, right? So 324 by zero point 0.5 is 648. So 648 is the maximum it can carry, right? So because it's rotating just about the horizontal axis, that calculation is wrong. That would come if it was rotating about a vertical axis, right? The ball is rotated on a horizontal circular path above about a vertical axis. So mg is this way and is rotating like this. So you don't have t minus mg. There is no mg here. Okay, there is only. So let's change that. This doesn't look correct, right? Let's change that. So T equals m omega square L. Therefore, you have T minus mg equals this. So omega square equals 324 times 2 times 2, right? So omega is 36, approximately is 36. Very simple. Okay. If it was about a vertical axis, then you will have this minus mg. Then it will introduce a minus mg, right? Because there's also gravity. When will you have the maximum tension? When it is directly at the bottom, because then it will add up, right? So then you will have the maximum. Okay. So having introduced this idea, right? Let's go to, then we introduce this rigid body dynamics, the two equation. V equals omega cross R, AT equals alpha cross R, AR equals omega cross V, right? So then we introduce this idea of moment of the momentum or angular momentum, R cross MV or R cross P. Moment of the momentum is the R cross that, moment of anything is R cross that anything. The moment of the momentum is r cross p, where p is the momentum, linear momentum. Angular momentum is r cross the linear momentum, right? Therefore, L is also a vector. R cross p is L. L denotes the angular momentum, right? Now, L is related to, we introduce this idea of moment of inertia, right? L equals I omega. L is in the same direction as omega. L equals I omega. I is, think of I as a scalar, so L equals I omega, right? Now, when you take the cross product, dl by dt will give you torque. Okay, torque is R cross, is the moment of the force. Okay, what happens to the second term? L equals R cross P, dl by dt is dr by dt cross P. Dr by dt is V. V cross P is 0. Why is V cross P 0? Because P is just M times V. So V cross V is 0. So you just end up with R cross dP by dt. R cross dP by dt is R cross A, right? Or R cross M times R cross A, or R cross MA dp by dt is what? Force. So r cross dp by dt ends up with being r cross f. So torque equals r cross f. Very simple. Okay. If you know the calculus well, then physics becomes very easy. Vectors plus calculus gives you physics, and therefore you have to understand it correctly. Okay. So conservation of angular momentum happens when there is no torque. Where do you deal with conservation of angular momentum, right? You deal with it in gravitation. This The second law of Kepler comes about because of conservation of angular momentum. What keeps the when a body is going in a circle, right, due to nothing but the gravitational attraction of one body. So the sun keeps a planet going in a, not a circle, ellipse. Okay, the, the sun is at the foci of the ellipse, and the planet is traveling in an ellipse, elliptical orbits around the sun. Heliocentric theory says that planets have elliptical orbits around the sun. Okay, so in that elliptical orbit, these planets go through the situation where their I omega stays the same, or I omega is r square omega. Okay, and r square omega, okay, mr square omega. I omega is mr square omega. I is mr square. You treat it as a point body. Okay, what is the moment of inertia about the sun? Mr square, right? So r square omega will be a constant. Mass of the body is a constant, right? So r square omega is a constant. R square omega is the same as the angular sweep. R square theta is basically the area, where if theta is what? Theta is the angle covered. Okay, so r square uh, d theta by dt will be a constant. So that is really Kepler's law. R square d theta by dt is a constant. Okay, therefore the angle swept will be a, he said that the angle swept r square d theta by dt will be a constant, or r square omega will be a constant. So the angle swept for equal times will be, or the area swept for equal times will be a constant. The areas, not the angle, the area swept at equal times will be a constant. So r square d theta by dt will be a constant, which is Kepler's second law, right? So the first law says bodies revolve around the sun, with the sun at one of the focus in an elliptical orbit. The second law says that the area swept, the angular area swept will be a constant. R square d omega will be r square d theta by dt, or r square omega will be a constant, right? That is the second law. The third law says t square is proportional to r cubed, and that can be derived by writing gmm by r square equals m omega square r. You write gmm by r square equals m omega square r, you will end up with t square is proportional to r cubed, which is the third law of Kepler. The square of the period is proportional to the cube of the average distance from the sun. Okay, cube of the average distance from the sun, because it's a elliptical orbit, right? Will give you the, or the cube of the semi-major axis. The square of the period will give you, is given by the cube of the semi-major axis. It's an amazing rule, and once you understand this, that t square is proportional to r cubed, then you can from that divine gravitation. In fact, okay, so that there is, if you have said that there is, if there is a force of gravitation, it is t square. T square is proportional to r cubed, tells you that gmm by r square is the force. Okay, so very related and beautiful ideas. And so I've dealt very quickly with a lot of complicated ideas here. And why I did it is so so that you get a very good basis for rotation. Next class, we will do some more problems dealing with rotation. But for today, remember dl by dt is tau external, right? It deals with external torque. So in the case of planetary motion, external torque can come if there is a passing body which imparts a some kind of a external force. In There's the sun, there's another planet, let's say there is a something else which comes, which also causes an attraction, then it will push something out of into a different orbit. And therefore these things were studied by this guy called Lyapunov. Lyapunov said that there is associated, why are the planets stable in stable orbits, right? And he said that there is a certain Lyapunov stability which keeps everything in balance. Okay, we will not go into Lyapunov stability, but we will discuss this idea of how these things play out. Okay, and but I've dealt with all the basic quantities in rotation except moment of inertia. Moment of inertia is just r square dm integral, but I will deal with that in the next class, because if I pump you with too much information, you will not follow all these details. Okay, so these are all the ideas that deal with with angular momentum. When there is no torque, there is conservation of angular momentum, just like in the case of linear quantities. When there is no force, there is conservation of linear momentum. Similarly, when there's no torque, there is conservation of angular. Okay. Now, there are a lot more ideas in rotation, but these are the basic ideas. Okay. Then we will introduce, taking moments, as to produce an extra equation in your in solving, like say the ladder problem, etc., and solving many struts problems that you learn that in engineering mechanics if you take engineering mechanics in college. Okay, so but for now, just learn these basic ideas, read the particular chapters from HC Verma, okay, along with your NCRT textbook. NCRT textbook is very good, but I like to tell students to do the problems in HC Verma. HC Verma helps if you're studying for NEET or JEE. The rotational chapter is rotational mechanics, chapter number 10. And right after chapter number 10, he discusses gravitation, chapter number 11. I discuss also these two a little bit together, but first I discuss these ideas. Rotation takes more than one class to complete, even when we are doing things very fast. Because next class we have to deal with power, we have to deal with rolling, and we have to deal most importantly with moment of inertia. But definitely read the two chapters, most notably chapter 10 in HC Verma, rotational mechanics, or the corresponding or the corresponding chapter in your NCRT textbook dealing with rotational mechanics. So read carefully, and then if you are using HC Verma, read the solved problems and then attempt some of the solved problems. In our case, students who are Jnanamarga students should download if you are planning for JE, download the JE app. If you're a CBSE 12 student, get the CBSE 12 app. If you're a GSEB student, get the GSEB 12 app. Learn the material. Then, okay, you will find our lectures as well as the IIT PAL lectures. With these two, you will do very, very well. And do problems. Once you've learned, then do problems. First, look at the solved problems. Then you look at the material. Have a notebook. Write the formulas. Rotation is full of formulas, full of ideas, quantities. So write the quantities, write the relationships, write the formulas. When we deal with it, we deal with slowly with the particular details. So having understood the details, you must remember, you must know the relationships, you must know the vectors, and you must know how to, then only you will know how to solve the problems. Become comfortable with the maths, comfortable with the quantities. Then you will know how to. Okay. With that, I'm going to stop. We will meet again um, next week uh, on Saturday morning, I deal with 11 physics. Sunday morning, I deal with the 12 physics. Okay, so keep that in mind. I'll see you again next class.